Now that we've talked about how electricity can produce magnetism, a magnetic field, and how changing magnetic fields can produce electric fields, we can talk about Maxwell's equations and electromagnetic waves. So first, first, before I go into Maxwell's equations, let me just write two constants that are going to come up in all of these equations, most of these equations. So you've seen these before, but this constant mu sub 0 is 4 pi times 10 to the minus 7. And I'm not going to give the units. I'm just going to say both of these are in SI units. So just don't worry about it because they're complicated. And then the other one is epsilon sub 0. And that's equal to 8.854 times 10 to the minus 12th, also in SI units. Okay, so those are there whenever you need them for calculations. So now I want to talk about Maxwell's equations. We're not really going to use these. I'm just sort of giving these to you because they're super important. They still, they're 150 years old, but they still describe all phenomena in electricity and magnetism. And so it's just a super important part of physics. Maxwell didn't come up with all of these equations himself. His main contribution was just unifying all of these into a single theory. And there was one major change that he made to one of the equations. So let me just go through the equations. So what did they do? They, first of all, unified electricity and magnetism. So it all became one totally contained theory. And when he put these together, it suggested something that was a big surprise and is kind of an amazing fact. And so there was one surprising suggestion. It wasn't proved by Maxwell's equations, but it certainly made this suggestion, and it ended up being proved later. Okay, so there's 4 equations in Maxwell's equations. The first one is called Gauss's law for electric fields. And I'm going to give you these, but like I said, these are not equations that you're going to use. They're, in general cases, they're very complicated to use, and even in simplified cases, they're pretty tricky to use. But the integral over a closed surface, you can imagine enclosing an amount of space in shrink wrap. That's what this integral means. And you take the integral of the electric field vector dotted with this vector dA, and it's equal to the enclosed charge divided by that constant epsilon 0. And so I'm just going to say that this provides restrictions on electric fields. And then there's a similar one for magnetic fields. So Gauss's law, the second one is Gauss's law for magnetic fields. And that says that the integral over a surface of the magnetic field vector dotted with dA is equal to 0. And then we get to 2 that we have done calculations with, but you haven't seen it in this form. That's okay. You don't have to get used to this new form. The only times we'll use these are the ways that we've used them so far. But Faraday's law of induction, and the full form of this, the integral over a closed path of the electric field vector dotted with, this is a line integral if you had a class where you talked about that, and this is equal to the negative derivative with respect to time of the magnetic field of the magnetic flux. Okay, so you remember seeing something like this, but it wasn't in this form. And this relates to how changing magnetic fields or really how a changing magnetic flux induces a current. And then the last one is the equation that Maxwell modified. So this is the Ampere-Maxwell equation. And this says that the integral over a path, a closed path of B dot ds is equal to the constant mu sub 0 times the current. Plus, the new thing that Maxwell realized is that this form, that's the way it was proposed by Ampere, would not work in the case of magnetic fields that are changing in time. If magnetic field vectors are changing in time, you can fix the problem by adding on this term. And this is the derivative with respect to time of the electric flux. Okay, so what Maxwell added was this idea of a displacement current. That's what's used in the second term on the right side. And the definition of this displacement current is the constant E sub 0 times the derivative of the electric flux with respect to time. This is really helpful, this idea, or necessary when you're dealing with capacitors that are charging or discharging. That's a case where the magnetic field and the electric field are changing in time. And so all you have to remember about that is that this new thing, this displacement current, is equal to the current going to and from each side of the capacitor. Okay, so that will come up in the assignment, but just remember you're going to have to use this definition. And what this equation gives us is how electric currents cause magnetic fields. Okay, well, since you have electricity producing magnetism and magnetism producing electricity, it wouldn't be too surprising to think that these start sort of a chain reaction where they propagate each other over and over. And that's the idea of electromagnetic waves. So if you have electricity producing magnetism and magnetism producing electricity, that's an electromagnetic wave. And so these four equations together are pretty complicated to work with. But if you make certain smart simplifications, people pretty quickly realized that you could figure out a lot about the nature of these electromagnetic waves. And so the special case that we're going to consider, so this simple special case, it's really not that simple, but it's a lot more simple than those equations can be in a fully general case. These are called plane waves. And here's what this looks like. So we have an x-axis, and that's the direction that this wave is going to propagate along. And we have a y-axis, and that is the direction of the electric field vectors are going to be parallel to the y-axis. And then we have a z-axis, and the magnetic field vectors are going to be parallel to the z-axis. And so here is what this wave looks like. So along the y-axis as we go, so the wave starts at time 0, it starts, say, at the origin and moves along the positive x-axis. And in time, you're going to get electric field vectors that look like this. And in sync with those, you're going to get magnetic field vectors. And remember, those are perpendicular to these electric field vectors. These are parallel to the z-axis. And so as time goes by, you get these kind of matching wave patterns along the y-axis for electric field vectors and along the z-axis for magnetic field vectors. So this is the electric field vectors, and the green are the magnetic field vectors. But you can see they have the same wavelength, same frequency. Okay, well, in this simplified case of plane waves, what people saw was that Maxwell's equations reduce to two differential equations. And again, I'm just writing these down so you can see them. You're not going to have to work with these or anything, but this is what they look like. The partial derivative, I know some of you have not seen partial derivatives, but just bear with me here. The second partial derivative of the size of the electric field with respect to time is equal to 1 over the constant mu 0 times the constant epsilon 0 times the second partial derivative of the size of the electric field with respect to x this time. Okay. And an almost identical equation for the magnetic field that says second partial derivative of the magnitude of the magnetic field with respect to time is equal to 1 over mu sub 0 times epsilon sub 0 times d squared of b over dx squared. Okay, those look pretty much identical. And those just fell out of the equations when people thought about them the right way. And this form is a very well-known equation called the wave equation. It was already called the wave equation. And so this is an equation that describes wave motion. And based on previous knowledge about the wave equation, it was immediately clear to people that the speed of this wave was going to be the square root of this constant that's multiplied by the right-hand term in both of these two equations. So what we get is that the speed of this wave is equal to 1 over the square root of mu sub 0 times epsilon sub 0. Okay, I gave you those two equations at the start. And here's the amazing thing that suddenly people became aware of. The speed of light had been measured already. This gave a way to calculate the speed that an electromagnetic wave would propagate through space. And this calculation came out to be exactly the speed of light to many decimal places. So I'm going to call this lowercase c, that's the speed of light. Okay. So before this, people didn't know that light was a type of electromagnetic wave. After this, it seemed very clear that there was a connection between these things, although people hadn't proved it yet. But it was hypothesized at this point and later proven that light is just a type of electromagnetic wave. And so different electromagnetic waves are categorized by their wavelengths. And so I'm just going to give you a little summary of information about the wavelengths of different types of electromagnetic waves. So these are all going to be classified by their wavelength. On the order of about 1 kilometer wavelength are AM radio signals. So radio signals also are a type of electromagnetic wave. On the order of about 1 meter of wavelength are FM radio waves. On the order of about a millimeter are infrared waves. on the order of about 1 micron, 1 micrometer, is the spectrum of visible light. At about the length of 1 nanometer is ultraviolet. And then finally, as you get around 1 picometer, we have first X-rays, and then as the wavelength goes down from there, we get to gamma rays. So these are the different categories of electromagnetic waves, but the only difference between them is the wavelength. Well, since electromagnetic waves behave like waves, they are waves in a way, although they can travel through empty space. That's a big difference between the mechanical waves that we talked about before. But we can use some of the old wave stuff that we know from before. Old wave equations. Okay, so here's some of the stuff that works perfectly well for electromagnetic waves. First, the wavelength is equal to the wave speed divided by f. And of course, here that wave speed is the speed of light. Second, for plane waves, we can assume a simple form of wave. They don't always have to have this simple form, but just like we did in mechanical waves before, we thought of the simplest type of wave that we could so that we could do some calculations. And so we can use the forms that the magnitude of the electric field is equal to that maximum value times the cosine of 2 pi over the wavelength times x minus 2 pi v over the wavelength times t. Okay, and so there are cases where you can use this equation to figure stuff out about the speed, the wavelength, and similar equation for the magnitude of the magnetic field. And then the final thing that you've seen before that we're going to keep using is the idea of intensity. Remember that intensity is equal to the power divided by the area that power is spread over. Now there are going to be 4 new equations that you haven't seen before. And these 7 equations all together are all you're going to need to use for these calculations. Let's see. So the first one is the one that I already introduced. That is for the displacement current. And remember that the displacement current, when you're dealing with a capacitor, is just the regular current going to the plates of the capacitor. And its definition is epsilon sub 0 times the derivative with respect to time of the electric flux. Okay, so there's an equation that, a problem that I will assign today, where it asks you to calculate the time rate of change, this this derivative with respect to time of this electric flux. Well, the way to do that is going to be to use this equation. You know from the current going to the capacitor what the displacement current is, and then just do the algebra to calculate that derivative. The second new equation is that at any given time, the ratio of the magnitude of the electric field divided by the magnitude of the magnetic field, well, this isn't true when B is equal to 0, but because that's undefined, is equal to the speed of light. So you can, if you have one of these two, E or B, you can use this equation to calculate the other one. And notice, since this is true at every instant, and these two waves are perfectly in phase with each other, this is also true at the maximum values. So you can also do this with the E max and B max values. Those are like the values that get used in number 2 of these wave functions. The third one is a new relationship with intensity. So remember, intensity is the power divided by the area. But it's also equal to this new thing, this capital S. And this S is called the magnitude of the pointing, that's a guy's name, pointing vector. And it has to do with energy flow. And we're going to see in the last equation, I'll give you last new equation, that this is something that we can use. There are other ways to calculate this. So this average value of the pointing vector, you can also calculate as the maximum value of the electric field squared divided by 2 times mu 0 times the speed of light. And since equation number 2 gives us a relationship between E max and B max, we can just do a substitution here and write it in a different form, and that is that C times B max squared over 2 times mu 0 is also equal to the intensity and also equal to that average pointing vector value. And then the last one is, this might be a little bit surprising, but electromagnetic waves hitting a surface apply a pressure to that surface, as if these waves aren't just waves in space, but also they're particles bumping into the surface. And so light hitting a surface causes pressure on the surface. And so these equations that I'm going to give you here are for an electromagnetic wave that's hitting a surface perpendicularly to the surface. It's a little more complicated if they're at an angle other than 90 degrees, but we're just going to use 90 degrees. So if the surface is a perfect absorber of electromagnetic waves, like think of a matte black surface. So this is perfect absorption. Then the pressure on the surface is equal to the magnitude of that pointing vector divided by the speed of light. And if, on the other hand, the surface is a perfect reflector of electromagnetic waves, like a mirror, then the pressure on the surface is equal to 2s over c. And this, if you're curious about this, you could think back to the first term of, Physics 1, where we talked about the impulse momentum equation, and it requires a bigger force to apply to something if you're making that object not only stop, but then go back to the same speed it had in the opposite direction. That takes more force, and that's what you're seeing here. If particles are being reflected from the perfect reflector, they not only have to go from their speed to zero, they have to go from their speed to zero and then from zero back to that speed going the other direction. That's where that 2 comes from. Okay, so let's do an example where we use some of these equations. And for all the complicated talk and complicated equations, remember everything is going to come from these 7 equations. Okay, and then the constants. So the 3 that we knew from waves before, and the 4 new equations for electromagnetic waves. Okay, so let's say that we have a wave, an electromagnetic wave with a frequency of 1 times 10 to the 15 hertz. So 1 times 10 to the 15th cycles every second. And let's say that we know that the maximum value of the electric field is 150 newtons per coulomb. And we want to figure out the following things. What's the wavelength? And can we identify what kind of electromagnetic wave that is? Second, can we calculate the intensity of this wave? Third, can we calculate the total force this wave would apply to a 10 meter by 10 meter square of area that's perpendicular to that wave? So we are assuming that the wave is perpendicular to this area. And then last, can we calculate the maximum value of the magnetic field vector? So we want to calculate Bmax. Well, first for the wavelength, we can just use the most familiar equation to us that has to do with waves, and that is that the wavelength is equal to the wave speed divided by the frequency. The wave speed is 3 times 10 to the 8th, the speed of light. The frequency was given as 1 times 10 to the 15th. And so we get 3 times 10 to the minus 7 meters. And it turns out that that is within the range of visible light, and a wavelength of 3 times 10 to the minus 7 meters is somewhere in the range of like a violet color. So if you see a wavelength like this, your eye is absorbing a wavelength in this ballpark. Now we want to calculate the intensity. We have a few equations for the intensity. So the intensity, we could do it as power divided by area, or if we could calculate the average value of the Poynting vector, we could use that. But the one that's most useful to us, just going down that list, is E max squared divided by 2 times mu sub 0 times the speed of light. E max is 150. So we're squaring that, dividing it by 2 times 4 pi times 10 to the minus 7. And then the speed of light. And we get an intensity of 93.75 watts per meter squared. Now to calculate the total force acting on this 10 meter by 10 meter square, we are told that, oh, and I didn't tell you this, but let's say that this area is a perfect absorber of that electromagnetic wave. I just forgot to write that before. Okay, so the equation for a perfect absorber is that the pressure is equal to S over the speed of light. And so since we already have the intensity, and the intensity is equal to the average value of that Poynting vector, that capital S, we can write this as the pressure is equal to, so I'm going to write this as, we're going to calculate this average pressure. Okay, and that average pressure is equal to the intensity divided by the speed of light. And you get a value of 3.125 times 10 to the minus 7th newtons per meter squared. And in order to go from pressure to force, we just have to multiply by the area. And so the average force that's applied is an area of 10 times 10 meters is 100 meters squared times the pressure, and you get a force of 3.125 times 10 to the minus 5 newtons. And then finally, we want to calculate the maximum value of the magnetic field vector. Well, we know that E max over B max is equal to C, so it's equal to 3 times 10 to the 8th. We know the value of E max, we're given that, so that's 150. And so we have rearrange this equation, and you get that B max is equal to E max over C. And so that's 150 divided by 3 times 10 to the 8th. And you get a value of 5.0 times 10 to the minus 7 Tesla. So as you're doing these, just remember that all of these calculations are contained in those 7 equations, And if you just have those equations in front of you, it should be easy to map out what I'm asking.